Hello friends, today we learn about eigenvalues, eigenvectors and quadratic forms. Introduction. In this module, we learn some very important and useful concepts of matrix algebra like eigenvalues, eigenvectors and quadratic forms. These concepts play a vital role in the theory of economics. The use of eigenvalues and eigenvectors is eminent in the study of various statistical and economic models, especially those dealing with solving system of linear differential equations. The problems of finding maxima or minima of functions of two or more variables occur frequently in economics. In such problems, we need to deal with finding the signs of the quadratic forms which arise through the second order conditions for maximality or minimality of functions at a point. In this sense, study of quadratic forms is quite important for economists. With this little motivation, we now introduce eigenvalues through the eigenvalue problem. The eigenvalue problem. Given a square matrix A of order n, the eigenvalue problem is to determine a non-zero column vector x equal to x1, x2 and so on up to xn in Rn and a real scalar lambda satisfying Ax equal to lambda x. We may interpret the eigenvalue problem as a problem of solving the system of n linear equations in two unknowns, a vector x and a scalar lambda. Such situations occur frequently in economics and econometrics. This leads us to the definition of eigenvalues and eigenvectors. Definition: eigenvalues and eigenvectors. Let A be a square matrix of order n. A real number lambda is called an eigenvalue of the matrix A if there exists a non-zero column vector x equal to x1 and so on up to xn in Rn satisfying Ax equal to lambda x. The vector x is called an eigenvector of the matrix A associated to the eigenvalue lambda. Later we shall see through an example that more than one eigenvectors can associate with the same eigenvalue lambda. Eigenvalues and eigenvectors are also known as characteristic roots and characteristic vectors of a matrix respectively. Let us now discuss the method of determining the eigenvalues and eigenvectors. Note that the equation Ax equal to lambda x is same as A minus lambda I x equal to 0, where I denotes the identity matrix of order n. But we know that the system of equations A minus lambda I x equal to 0 has a non-zero solution if and only if the determinant of the matrix A minus lambda I is 0. Thus, if we denote the determinant of A minus lambda I by mod A minus lambda I, then the eigenvalues of the matrix are simply the roots of the equation mod A minus lambda I equal to 0. This equation is known as the characteristic equation of the matrix A, whereas mod A minus lambda I, which is a polynomial in lambda of degree n, is known as the characteristic polynomial of the matrix A. Here it is worth mentioning that every matrix satisfies its characteristic equation. In other words, if f of lambda is equal to mod A minus lambda I denotes the characteristic polynomial of the matrix A, then f of A is equal to 0. This result is known as Cayley-Hamilton theorem and it is often useful in computing the higher powers of matrix A or its inverse if it exists. Now, since mod A minus lambda I is a polynomial in lambda of degree n, the characteristic equation of a matrix A of order n has at the most n real roots in general. Note that it is very much possible that a polynomial of an even degree has no real roots, and so a square matrix of an even order may not have any real eigenvalues. However, if the matrix is symmetric, then it can be proved that its characteristic equation has exactly n real roots, which may not be necessarily distinct. Thus, we can say that if A is a square matrix of order n, then it has at the most n eigenvalues, and further if A is symmetric, then it has exactly n eigenvalues, which are usually denoted by lambda 1, lambda 2 and so on up to lambda n, but not necessarily distinct. Let us now consider some examples about computing the eigenvalues and eigenvectors. Example 1. Determine the eigenvalues and eigenvectors of the matrix A of order 2 whose rows are 9 2 and 2 6. Solution. Here the characteristic equation of the matrix A is mod A minus lambda I equal to 0, which on expansion of the determinant is same as lambda square minus 15 lambda plus 50 equal to 0. But lambda square minus 15 lambda plus 50 is same as lambda minus 5 into lambda minus 10, and hence the eigenvalues of A are lambda 1 equal to 5 and lambda 2 equal to 10. In order to determine an eigenvector associated to the eigenvalue lambda 1 equal to 5, we have to solve the matrix equation A minus 5I into x equal to 0, which is same as solving the pair of equations 4x1 plus 2x2 equal to 0 and 2x1 plus x2 equal to 0. Since these two equations are identical, any non-zero vector x1 x2 in which x2 is equal to minus 2x1 is an eigenvector of A associated with the eigenvalue 5. Similarly, for finding an eigenvector associated to the eigenvalue lambda 2 equal to 10, we have to solve the matrix equation A minus 10I into x equal to 0, which is same as solving the pair of equations minus x1 plus 2x2 equal to 0 and 2x1 minus 4x2 equal to 0. Thus, any non-zero vector x1 x2 in which x1 is equal to 2x2 is an eigenvector of A associated with the eigenvalue 10. We saw that there are infinitely many eigenvectors associated with the eigenvalues 5 and 10 of matrix A. However, if we insist on eigenvectors of unit length, then they are 1 upon root 5 minus 2 upon root 5 and minus 1 upon root 5 2 upon root 5 associated to the eigenvalue 5, and those associated to the eigenvalue 10 are 2 upon root 5 1 upon root 5 and minus 2 upon root 5 minus 1 upon root 5. Now, we consider an example of a matrix of order 3. Example 2. Determine the eigenvalues and eigenvectors of the matrix A of order 3 whose rows are 1 0 0, 0 2 0 and 0 0 1. Solution. It is easily observed that the characteristic equation of the matrix A here is 1 minus lambda into 2 minus lambda into 1 minus lambda equal to 0, and hence the eigenvalues of A are 1, 2 and 1. Note that although we have a matrix of order 3, we have only 2 distinct eigenvalues. For eigenvectors corresponding to the eigenvalue 1, we solve the matrix equation A minus I into x equal to 0, and this gives x2 equal to 0. Thus, any non-zero vector x1, x2, x3 in which x2 is 0 is an eigenvector of A associated with the eigenvalue 1. On the other hand, it may be verified that the eigenvectors corresponding to the eigenvalue 2 are non-zero vectors x1, x2, x3 in which x1 is equal to x3 is equal to 0. It is clear from example 2 that the eigenvalues of a diagonal matrix are simply its diagonal elements. We now record few more interesting results regarding the eigenvalues and eigenvectors. Theorem: if lambda is an eigenvalue of a square matrix A, then it is also an eigenvalue of its transpose matrix A to the power t. Theorem: if lambda is an eigenvalue of an invertible or non-singular matrix A, then lambda inverse is an eigenvalue of its inverse matrix A to the power minus 1. Theorem: if lambda is an eigenvalue of a square matrix A, then lambda to the power k is an eigenvalue of the matrix A to the power k for every positive integer k. Theorem: let A be a square matrix of order n, then the eigenvectors corresponding to the distinct eigenvalues of A are linearly independent vectors. In addition to these results, if A is symmetric, then we have some additional information regarding its eigenvalues and eigenvectors. Theorem: let A be a symmetric matrix of order n, then real eigenvalues of A exist, and further if lambda 1, lambda 2 and so on up to lambda r are its distinct real eigenvalues, which are repeated k1, k2 up to kr times respectively, then k1 plus k2 and so on up to kr is equal to n. Theorem: let A be a symmetric matrix of order n. If q1 and q2 are the eigenvectors corresponding to the distinct eigenvalues lambda 1 and lambda 2 of A, then q1 and q2 are orthogonal vectors. Theorem: let A be a symmetric matrix of order n, and suppose lambda 1, lambda 2 and so on up to lambda r are its distinct real eigenvalues, which are repeated k1, k2 and so on up to kr times respectively. Then for each j which is greater than equal to 1 and less than equal to r, there exists kj mutually orthonormal eigenvectors associated with the eigenvalue lambda j. Further, the matrix P formed by this n mutually orthonormal eigenvectors is orthogonal, and P inverse AP equal to lambda is a diagonal matrix whose diagonal elements are simply the eigenvalues of A. In the above theorem, since P inverse AP produces a diagonal matrix, we often say that P diagonalizes the symmetric matrix A. As diagonal matrices are easy to deal with in many scenarios, the last theorem leads us to the topic of matrix diagonalization. The diagonalization of a square matrix. Definition: similar matrices. Let A and B be square matrices of the same order. If there exists an invertible matrix P such that P inverse AP is equal to B, then we say that A is similar to B. Note that if P inverse AP is equal to B, then by taking Q is equal to P inverse, we have Q inverse BQ equal to A. Thus, A is similar to B if and only if B is similar to A. And so, we also use the terminology A and B are similar matrices instead of A is similar to B or B is similar to A. Similar matrices share many properties, and perhaps that is the reason they are called similar. It is not difficult to prove that similar matrices have same determinant, trace, eigenvalues and rank. Also, since matrix multiplication is associative, for every positive integer n, b to the power n is equal to p inverse a to the power n into p, and a to the power n is p into b to the power n into p inverse. Now, for a diagonal matrix, since the computation of its determinant, rank, powers and other such things is a very simple task, we are often interested in knowing whether the given matrix is similar to a diagonal matrix or not. This leads us to the definition of diagonalizable matrix. Definition: diagonalizable matrix. Let A be a square matrix, then it is called a diagonalizable matrix if it is similar to a diagonal matrix, or in other words, if we can find an invertible matrix P such that P inverse AP is a diagonal matrix. The process of finding such P for the matrix A is called matrix diagonalization. The above definition raises an immediate question: is every square matrix diagonalizable? The answer to this question is given by the following technical theorem. Theorem: let A be a square matrix of order n. Then A is diagonalizable if and only if it has n linearly independent eigenvectors. Since we have seen in one of our earlier theorems that the eigenvectors corresponding to distinct eigenvalues are linearly independent, we have the following nice result. Theorem: let A be a square matrix of order n. Then A is diagonalizable if it has n distinct real eigenvalues. In view of the last theorem about symmetric matrix above, we can say that every symmetric matrix is similar to a diagonal matrix whose diagonal elements are its eigenvalues. Since the trace and determinant of a diagonal matrix are respectively the sum and product of its diagonal elements, it follows that the trace and determinant of every symmetric matrix is respectively the sum and product of its eigenvalues. We now consider an example to understand the matrix diagonalization process. Example 3. Diagonalize the matrix A of order 3 whose rows are 3, -1, 1, -1, 5, -1 and 1, -1, 3. Solution: the characteristic equation of the matrix A is mod A minus lambda I equal to 0. Expanding the determinant and simplifying, it gives lambda cube minus 11 lambda square plus 36 lambda minus 36 equal to 0, whose roots are 6, 3 and 2, and these are the eigenvalues of A. In order to diagonalize the matrix A, we have to determine the orthogonal matrix P whose 3 columns are the orthonormal eigenvectors corresponding to the eigenvalues 6, 3 and 2. For the eigenvector corresponding to the eigenvalue 6, we solve the matrix equation A minus 6i into x equal to 0. It may be verified that one of the solution of this system of equations is x1 is equal to 1, x2 is equal to -2 and x3 is equal to 1. Thus, V1 equal to 1, -2, 1 is one of the eigenvector of A associated to the eigenvalue 6. Similarly, it may be verified that V2 is equal to 1, 1, 1 and V3 is equal to 1, 0, -1 are the eigenvectors of A associated to the eigenvalues 3 and 2 respectively. Therefore, the orthogonal matrix P which diagonalizes A is given by the matrix P of order 3 whose rows are 1 upon root 6, 1 upon root 3, 1 upon root 2, -2 upon root 6, 1 upon root 3, 0 and 1 upon root 6, 1 upon root 3, -1 upon root 2. It may now be verified that P inverse AP which is equal to P transpose AP is the matrix whose rows are 6, 0, 0, 0, 3, 0 and 0, 0, 2. Let us now discuss the role of eigenvalues in the study of quadratic forms. Quadratic forms definition: quadratic forms. Consider a square matrix A equal to Aij of order n and a column vector x equal to x1, x2 and so on up to xn in Rn. Then the quadratic form associated with the matrix A equal to Aij is an expression of the form Qx equal to x transpose Ax equal to double sum running over I equal to 1 to n and j equal to 1 to n of aij xi xj. Remark, if A is not symmetric, then by defining aij star as aij plus abi upon 2, which is same as aji star, we see that quadratic form q star x associated with the symmetric matrix A star equal to aij star is same as the quadratic form qx associated with the non-symmetric matrix A. This is the reason we may confine our attention to the study of quadratic forms associated with this symmetric matrix only. Example 4. Determine the quadratic form associated with this symmetric matrix A of order 3 whose rows are 3, minus 1, 2, minus 1, 1, 4 and 2, 4, 5. Solution. Here qx equal to x transpose Ax is equal to 3x1 square plus x2 square plus 5x3 square minus 2x1 x2 plus 4x1 x3 plus 8x2 x3. We now introduce the terminology related to the sign of quadratic forms. If qx equal to x transpose Ax is greater than 0 for all non-zero x, then we say that the quadratic form qx is positive definite and the matrix A is said to be a positive definite matrix. If qx equal to x transpose Ax is greater than equal to 0 for all x, then we say that the quadratic form qx is positive semi-definite and the matrix A is said to be a positive semi-definite matrix. If qx equal to x transpose Ax is less than 0 for all non-zero x, then we say that the quadratic form qx is negative definite and the matrix A is said to be a negative definite matrix. If qx equal to x transpose Ax is less than equal to 0 for all x, then we say that the quadratic form qx is negative semi-definite and the matrix A is said to be a negative semi-definite matrix. If a quadratic form takes positive as well as negative values, then it is said to be indefinite. The following theorem gives a necessary and sufficient condition for determining the definiteness of a given quadratic form. Theorem. Let qx be a quadratic form associated with a symmetric matrix A. Then 1. Qx is positive definite if and only if all the eigenvalues of A are positive. 2. Qx is semi-definite if and only if all the eigenvalues of A are non-negative. 3. Qx is negative definite if and only if all the eigenvalues of A are negative. 4. Qx is negative semi-definite if and only if all the eigenvalues of A are non-positive. 5. Qx is indefinite if some of the eigenvalues of A are positive and some of them are negative. We now see one application of quadratic forms. Theorem. For a real valued function y equal to f of x1, x2 and so on up to xn, if a point x star equal to x1 star, x2 star and so on up to xn star is a point of local minimum or local maximum, then gradient of f at x star is equal to 0. Further, if H is the Hessian matrix evaluated at the point x star, then the point x star is the point of local minimum or maximum accordingly as the quadratic form d square y equal to dx transpose h dx is positive or negative definite. On the other hand, if the quadratic form dx transpose h dx is indefinite, then x star is neither the point of local minimum nor the point of local maximum. Finally, let us consider one example to understand this. Example 5. Determine the points of local extremum for the function y equal to f of x1, x2 which is equal to x1 cube upon 3 plus 3x1 square plus x1 into x2 plus x2 square upon 2 plus 6x2. Solution. Here f1, which is del y by del x1, is equal to x1 square plus 6x1 plus x2, and f2, which is del y by del x2, is equal to x1 plus x2 plus 6, and so gradient of f equal to 0 comma 0 gives x1 square plus 6x1 plus x2 equal to 0 and x1 plus x2 plus 6 equal to 0, whose solutions are 1 comma minus 7 and minus 6 comma 0. Now, the Hessian matrix H of order 2 has rows as 2x1 plus 6 1 and 1 1, and so H at the point 1 comma minus 7 is the matrix 8 1 and 1 1. The eigenvalues of this matrix are roots of the equation mod 8 minus lambda 1 and 1 1 minus lambda equal to 0. But this is same as solving the quadratic equation lambda square minus 9 lambda plus 7 equal to 0, whose roots are 9 plus root 53 upon 2 and 9 minus root 53 upon 2. Since both these roots are positive, we conclude that H is positive definite at the point 1 comma minus 7, and so 1 comma minus 7 is the point of local minimum for the function f. It may be verified that the Hessian matrix at the point minus 6 comma 0 has one positive and one negative eigenvalue, and hence the point minus 6 comma 0 is neither the point of local minima nor the point of local maximum. Summary. We introduced the concept of eigenvalues and eigenvectors through the eigenvalue problem and discussed the method of computing eigenvalues and eigenvectors of a square matrix. We showed how a symmetric matrix can be diagonalized through an orthogonal matrix which is constructed with the help of its orthonormal eigenvectors, and discussed the importance of such diagonalization process. In the final part of this module, we tried to understand what quadratic forms are and how they are linked with the concept of eigenvalues while studying the nature of extreme points